All right, let's just dive right into this. Welcome to today's explainer. We're tackling a problem that literally every software engineer or really any data hoarder faces, but usually just tries to ignore. What on earth do you do with years of messy, unstructured data? You know the stuff. Chronological archives of markdown files, raw JSON payloads, random code snippets just sitting there. Well, today, we're looking at a fascinating case study that takes exactly that kind of digital clutter and completely transforms it into an AI architectural genius. We're going to explore the actual graph structure behind RAG, that's Retrieval-Augmented Generation, and see how it can literally design a system capable of handling 100,000 requests per second. Let's get into it. So here's our roadmap for today's explainer. First, we'll look at standard RAG's missing links, then preparing the raw data, extracting the knowledge graph, the GraphR reasoning engine, and finally, seeing how GraphR answers complex questions.
All right, starting with Section 1, Standard RAG's missing links. Let's look at why Standard RAG falls short when you're querying a massive, sprawling archive.
So the core difference here comes down to how we actually retrieve information. Standard RAG, which relies on your traditional vector search, is basically just keyword hunting. If you ask a really complex system architecture question, Standard RAG might find one disconnected snippet about databases over here, and maybe another one about APIs way over there. It completely fails when a query requires understanding how disparate technical decisions actually link together across an entire ecosystem. GraphRAG, on the other hand, performs multi-hop structural path traversal. It doesn't just look for words, it navigates an interconnected map of concepts. It's a total game changer. Moving on to Section 2, preparing the raw data, because before we can traverse a map, we actually have to build it.
Okay, a crucial rule of thumb here. You can't just dump garbage into an AI and expect gold, right? In our source material, the developer initially tried feeding raw JSON archives, stuff like YouTube video metadata, GitHub projects, and article dumps directly into AST-based code parsers. Now, those are meant for actual programming syntax. The result? The engine thought it was source code and produced exactly 0 semantic nodes. Total failure. To fix this, they actually built a custom automated Python transformer script. This script parsed the JSON and outputted clean, structured markdown documents with explicit headers and front matter. This one step gave them 525 clean documents fully primed for the next phase.
Which brings us to Section 3, extracting the knowledge graph. This is where we actually extract the semantic map of the data. The extraction metrics here are pretty incredible to look at. Using an OpenAI-compatible model called GPT-5.6 Luna, the system extracted 426 distinct nodes and 353 relationships between them. It even went a step further and detected 111 topic clusters using the Lighten algorithm. So this isn't just a list of words anymore, it's a living, breathing network of technical concepts. And get this, 93% of those relationships were explicitly extracted from the text, with the remaining 7% intelligently inferred by the model.
So what actually happens when you structure data this way? Well, the AI didn't just find random tags. It uncovered the core architectural pillars of this engineer's entire body of work. It found heavy connection clusters around things like ClickHouse and streaming ingestion, RAG and vector stores, Keycloak and OpenFGA for security, and modular Go architecture. The data is now structured around real, tangible engineering themes rather than just text.
But we run into a bit of a mathematical trap here, known as hub node distortion. Basically, if you use standard similarity metrics, two completely unrelated articles might get a perfect similarity score simply because they both happen to use a massive generic tag like machine learning. To fix this, the developer used the Adamic-Adar similarity algorithm. Think of it like this. If two articles share a super rare, highly specific connection, say ClickHouse Kafka engine, the algorithm gives that a massive weight. But if they only share a broad umbrella tag, that weight drops to near 0. This ensures the connections in the graph are highly confident and, most importantly, actually useful.
All right, Section 4, the GraphRAG reasoning engine. Now that we have our graph, how do we navigate it?
So how does this theoretical map become a functioning engine? Well, when a user asks a question, remember, standard RAG just hunts for text. But this custom GraphRAG engine uses breadth-first search, or BFS. It takes a seed entity from the user's query, let's say Kafka, and expands outward from it, pulling in all the closely related nodes and relationships. It builds this rich, highly specific, connected subgraph. It then feeds that targeted map straight to the LLM, giving the AI the exact structural context it needs to reason through a complex problem.
And that leads us to Section 5, GraphRAG answers complex questions. Let's put this to the ultimate test.
The prompt given to this custom assistant was incredibly demanding. It was asked, how can we design a software architecture capable of handling 100,000 requests per second? Now, answering that requires traversing dozens of interconnected concepts. It is definitely not a one-keyword answer. Let's see how the engine actually synthesized a blueprint from those 525 isolated blog posts.
Right out of the gate, the AI realized that at 100K RPS, a synchronous monolith is just going to fail. The blueprint it pulled together is striking. For the edge layer, it grabbed Cloudflare workers to aggressively offload requests and handle routing before traffic even touches the origin. For the core API, it mandated a go-clean architecture, utilizing CQRS to split the read and write paths. And for the data layer, it recognized that direct synchronous database hits are a huge bottleneck, so it proposed Redis for sub-millisecond in-memory reads, and ClickHouse for flat, columnar analytics.
And it honestly didn't stop there. The graph mapped out the entire asynchronous heartbeat of the system. It pulled the Kafka ingestion pipeline, using a polar dispatcher worker pattern to absorb massive write spikes without crashing everything. For security, it linked Keycloak and OpenFGA, specifically noting that OpenFGA's Zanzibar pattern is absolutely essential for low-latency authorization at high scale. Finally, for observability, it mandated OpenTelemetry and Sentry, because at 100K RPS, the unknown is what'll really kill you.
The AI managed to synthesize all of this into one cohesive thesis. To hit 100K RPS, you need a decoupled, event-driven, layered system that aggressively offloads work from the hot path. By eliminating synchronous I/O, using Redis to absorb heat, and Kafka to buffer bursts, every single component scales independently. The wild part? The GraphRAG engine didn't hallucinate any of this. It logically traced these connections through the author's own isolated articles to build a unified, brilliant strategy.
So why does the graph structure behind RAG actually matter so much? Because it enables some incredibly powerful applications for your own data. In this case study, it powered interactive front-end navigation, meaning readers could see genuinely related posts based on actual architectural topology, not just overlapping keywords. It enabled a deeply context-aware chatbot, and maybe most importantly, it allowed the author to audit their own knowledge gaps. The graph explicitly surfaced 256 isolated concepts and thin communities, immediately giving them a roadmap for what they need to research and write about next.
Which brings us to our final thought for today's explainer. If taking a scattered, simple blog archive and applying a graph structure to it can seamlessly map out the blueprint for a highly complex 100K RPS architecture, what kind of hidden intelligence is currently trapped in your company's unstructured data? It's probably just waiting for the right connections to be drawn. Thanks for joining me on this deep dive into GraphRAG. I highly encourage you to start looking at your own data not just as a pile of documents, but as an interconnected map just waiting to be explored.